We're going to apply Ampere's law to find the magnetic field of a long current carrying conductor both inside and outside. First, let's review electrostatics. A conductor that is not carrying a current has all of its excess charge on the surface. It's an electrostatic equilibrium. Therefore, there is no electric field within a conductor that is not carrying a current. However, if we do have a current, the charges are moving within the conductor due to the electric field created by the battery. So we do have an electric field in there. Using Ampere's law, we won't be able to say just the magnetic field within the conductor is zero, which is good because there is a magnetic field within a current-carrying conductor. A similar math technique that was used to calculate the electric field within an insulator with a uniform distribution of charge will be used here. Here's our conductor, this tube here. And first we'll find the magnetic field outside the conductor. Even though we already know it, we're just going to go over it again. We're going to take a distance r, which is greater than the radius r of the conductor. We construct an Amperian loop as shown. That's that disk there in the dashed lines. And on the loop, the magnetic field has a constant magnitude and is parallel at all points to ds. We've shown that before when we went over Ampere's law. So B dot ds will just be the magnitude of B times ds. We have Ampere's law, where we have a line integral about the Amperian loop, and B dot ds reduces to B ds. B is a constant, it comes outside, and the right-hand side, the enclosed charge, will be I. That's the current that's going through this loop, okay? We integrate ds over the circumference, we get 2 pi r. We divide through and we find the magnetic field, and this is a known result to us, so that's good that this works. And let's see, we show the magnetic field circling the conductor. Okay, so now let's do it inside the conductor. This time we draw the Amperian loop inside the conductor, where little r is less than big R. Once again, on the loop, the magnetic field has a constant magnitude and it is parallel at all points to ds. So we have B dot ds equals B ds. So it looks like our left-hand side of Ampere's law will be the same. What about the right? This time, the Amperian loop only surrounds some of the current in the wire. We're assuming it to be uniformly distributed, which again, that's just what we did with an insulator when we used Gauss's law to find the electric field. So this time, instead of talking about charge density and doing all the work, we're just going to say, let's just ratio the areas. It's the same answer. So the surface area of this Amperian loop here, because we're dealing with the surface area that the current's going through, that surface area is pi r squared. The overall surface area, if I take an Amperian loop that extends out to the width of the conductor, that's pi big R squared. So the current inside the smaller one is going to be pi r squared over pi big R squared. Pi's come out, and this will be our enclosed current. Start with the Ampere's law again, right here. And the left side looks just the same as when we did the magnetic field outside the conductor. The only difference is this I enclosed, which we calculated on the previous slide. Once again, B comes out. We integrate ds, a line integral over the entire Amperian loop. We get 2 pi r, do a little algebra, and here's our answer. So that looks like a linear function, right? Because the only variable there is little r. So the magnetic field is 0 in the middle of the conductor, and when little r equals big R, it is equal to the value that we obtained for the magnetic field outside the conductor. So it's continuous. That's good.